Welcome to Lecture 16 for Chemistry 312. This lecture is on nuclear reactors and radiochemistry in reactors, and it's in two parts. The readings for Lecture 16 are linked to the webpage, and it's Radiochemistry in Light Water Reactors, Chapter 3. The lecture, Part 1, is going to cover an overview of reactors. We're going to go into the basic concept of reactors, fundamentally that fission produces heat, which is then used to achieve some means, generally electricity production. And then we're going to discuss the different types of reactors. Some of them are divided by the type of water that are used, light water, where the uranium is enriched, or heavy water, where the water is enriched. A metal-cooled reactor, so for instance sodium or lead can be used as a coolant. This changes the energy of the neutron. The light water and heavy water reactors will slow down the neutron. Metal-cooled reactors, the neutron doesn't get slowed down. So you have different properties. You have a fast reactor and a thermal reactor. We'll also talk about gas-cooled reactors as opposed to liquid metal or water as the coolant. Gas is a coolant. Molten salt reactors, where the coolant and the fuel itself is combined. In this case, the molten salt reactor, uranium chlorides, uranium fluorides have been used. The fuel itself is melted. It's contained in a vessel. That's one primary concept. All the reactors we've talked about have been developed, have been tested. Light water and heavy water reactors are currently the bulk of the power reactors. There have been gas-cooled reactors, molten salt reactors made, and certainly there's been metal-cooled reactors, so sodium-cooled, uranium-fueled, fast reactors. And then we're going to end part one talking about space reactors. We'll talk about the properties of reactors that can be used for space propulsion. And this is gaining interest. It tries to explore methods for getting to Mars and planets beyond Mars. Part two, we're going to go into what occurs in the chemistry in these reactor systems and how that information is used to get some understanding on the reactors.
Nuclear reactors, regardless of the types, have some common properties. One is the fuel. All reactors have fuel. They're usually uranium isotopes, primarily in light water reactors, enriched uranium-235. However, plutonium isotopes can also be used in MOX fuel, and their chemical forms can either be oxides, metal, nitrides, or even salt in a liquid form. However, the main commonality is the use of a fissile isotope that is used to drive fission and produce heat. And since this heat is produced, the reactors also need to be cooled. There's a number of different routes for cooling the reactor. They can include air, water, other gases such as carbon dioxide, helium, or even a liquid metal such as sodium. Most reactors have some sort of cladding material which separate the fuel from the coolant. An exception to this is molten salt reactors, in which these reactors the fuel itself is molten, and it's contained often in a large vessel. Nuclear reactors will also contain moderators, in which the neutrons are slowed down in energy. This decrease in energy tends to increase the cross sections for the reactions with the fissile isotopes, for instance uranium-235. Not all reactors have moderators. Fast reactors rely upon fast neutrons, so they tend not to have the moderators. But example of the moderators can be protons, such as light water reactors, carbon. For instance here, this is a picture of the Chicago Pile 1, the first nuclear reactor, in which graphite was used as the moderator. Carbon needs more collisions more collisions to bring a neutron to thermal energy than a proton, so it's less effective. However, carbon does have a smaller reaction cross-section than protons with neutrons. Heavy water can also be used as a moderator and a coolant. The example with these are the CANDU reactors. One of the advantages of a heavy water reactor is that one does not need to enrich uranium. The isotopes of 235 from natural uranium is sufficient. And this is due to the fact that deuterium has a small neutron absorbance cross-section compared to proton. As I stated earlier, the first reactor is the Chicago Pile 1, the CP1, and this demonstrated a number of the properties that we discussed here. It was a graphite moderator. It was purified from boron, since boron has a large neutron capture cross-section. Cadmium was used as a control to control the reaction with the neutrons. There was also moisture that was used to control, and it was an air-cooled reactor, and it gave off about 2 kilowatts of heat. The heat from the reactors are used to produce electricity. So if the fission from the fuel, as we learned earlier, produces around 200 MeV of energy, and that energy is used to drive a turbine, which is then used to produce electricity. An example of a typical fuel rod, as we'll discuss in more detail later, for a light water reactor is shown here, where you have uranium with a cladding material, as we discussed. There's a gap between the cladding material and the uranium fuel. This allows some of the changes that are induced from the fission process in the uranium fuel to not influence the cladding material. The reactor materials also have similar characteristics. One is that they need to be compatible with the coolant, often water. However, salts can also be used as a coolant, and the materials need to be compatible with these materials. The compatibility needs to be durable at a high temperature. For instance, water is at about 300 degrees in pressurized water reactors during operation. They need to be resistant to corrosion. For obvious reasons, you wouldn't want the material producing particles that then go into the reactor, or breaking and causing coolant or even the fuel itself to be released. They need to have minimal interactions with neutrons, since the neutrons are the driving force in the production of power through the fission process. They need to be compatible with the burnable poisons. So the burnable poisons are compounds that are put into the reactor to help control the neutrons. For instance, boron can be a burnable poison. These burnable poisons can be both in the water and in the fuel, depending upon the reactor type. The materials need to have high strength, and they need to be resistant to hydrogen embrittlement. In a reactor, we generally have the fuel confined to a specific region. In light water reactor fuels, an example is shown here. You have a fuel pellet, which is a cylinder of uranium dioxide, and it's usually clad by some material. This cladding material is designed to separate the fuel from the solution. So the coolant, generally water. So in this case, we have this region where the fission is occurring. Fission products are being formed. They're impinging upon the fuel. They're forming different phases. The fuel's undergoing stress. It can crack. You can have some swelling as the fuel swells, as the fission gases increase. It can push out against the cladding material, and this can drive some potential interactions. One interaction is initiate stress corrosion cracking, where if you have the fuel begin to crack and it's pushing up against the cladding material, that crack can then propagate out to the cladding. Another interaction, once we have some interface between the fuel and the cladding, the chemistry of the fuel can start influencing the cladding. So if you start making elements that start having larger reactions with your cladding material, which is generally a zirconium-based material, you can start changing the chemistry of the cladding material and the fuel itself right at that interface. So this stress corrosion cracking is an effect, and this chemical interaction, the fuel cladding chemical interaction. Another example of some changes in the chemistry. This is a U3Si kernel, so uranium silica, which is people are looking at as a fuel. This material is in some zirconium cladding, so this material is basically interdispersed in the zirconium, and this would form a pellet that would then slide into this cladding material. And as you can see, upon irradiation, we have some changes in the chemistry, which is observed microscopy. So you get some interaction between the zirconium material and the uranium silica material. That's really driven by the fact that you're producing fission products, and it's those fission products that are interacting. Now, of course, the knowledge of the chemistry is useful in events where the fuel is outside of the cladding. So if the fuel escapes the cladding and goes into a coolant, understanding the chemistry of the fission products in this aqueous solution is important to understand its ultimate behavior. Now, there is a type of reactor that's shown here. This is a fuel for a molten salt reactor. They differ in the sense that they're not in cladding, but they're in vessels. So imagine that you start off with this would be a crystal, and this is a lithium, beryllium, uranium fluoride. As it heats up, it melts, and then you could have this in a vessel, and the liquid acts as its own coolant. It circulates, so you basically replace the cladding on each pellet with a large vessel that acts as a cladding for this entire solution. So molten salt reactors, we're not going to discuss them in detail, but the same sort of chemistry would go on. As I begin to fission this uranium and I make fission products, how are those fission products going to interact with the fluorides? So as opposed to the oxides in uranium dioxide, or the silicon in the U3Si, you've got the fluorides that are also going to influence the chemistry in these fluoride solutions. You also have conditions where radionuclides are generated in structural material. This is due to neutron capture. For instance, if you have a material, often stainless steels, contain cobalt-59, a neutron activation, that cobalt-59 is going to produce cobalt-60, and that cobalt-60 is going to be fundamentally embedded into that material. And how much material you're going to produce is obviously dependent upon the cross-section and the number of neutrons that are interfacing with this material. A typical example of a power reactor is a pressurized water reactor, also called PWR, and it is shown here. This is Westinghouse designed. You can see where you have the fuel rods, inlet for coolant, outlet for coolant. There's around 70 of these pressurized water reactors operating in the US. The vessel height and diameters are shown here, so they're rather large, on the order of 12 meters. The weight is on the order of 250 to close to 600 metric tons. The pressure, as it's implied, a pressurized water reactor has a maximum pressure of 2,500 psi and a maximum operating temperature of around 350 degrees C. And a schematic of this reactor, and very similar to other power reactor designs, are shown here, where the heat is generated in the reactor vessel. The coolant from the reactor travels to a loop where a secondary loop of, in this case, water, transfers the heat, produces the steam. This steam turns a turbine. The water condenses and continues to loop around. So you do not use the initial coolant water from the reactor to drive the turbine. Use a secondary loop. One design that does use the actual reactor vessel coolant are reactors that are used in submarines, and this is due to the space confinement. Information on a pressurized water reactor fuel assembly is provided here. There's typically on the order of 250 fuel rods per assembly, around 500 kilograms of uranium. Each rod is on the order of 3.7 meters. And the amount of power that a pressurized water reactor can produce is based upon its size, and it goes anywhere from 600 megawatts electric to 1,500 megawatts electric. And just as a note, the amount of thermal power that is produced is on the order of it's about 3 times the amount of the electrical power. The core of these reactors are shown here. The diameters are on the order of 2.5 to 4 meters, and the total number of fuel assemblies, so again there's around 250 fuel rods per assembly, and the total number of assemblies per reactor can vary from 120 to around 250. Another type of light water reactor is shown here as a boiling water reactor. There's about 35 operating in the United States. And a boiling water reactor operates at a pressure of about 1,100 pounds per square inch, and with the water boiling at the core at a temperature of around 285 degrees C. There are control rods located in the center of a 4-assembly cluster of fuel assemblies. So this control rod's used to control the neutrons and thereby the energy of the reactor. They're normally operated on a 3-year cycle, and about 1/3 of the core fuel is discharged annually. For a boiling water reactor, 1,000 megawatt electric boiling water reactor has about 100 metric tons of heavy metal. That's usually defined as uranium. The reactivity is controlled with burnable poisons added to the fuel, for instance gadolinium dioxide. And this gadolinium, as a burnable poison, it has a large neutron capture cross-section. When the reactor starts, there's often, in the initial phase of the reaction, there's often an excess of neutrons. This gadolinium absorbs those excess neutrons. The reactor power can also be controlled by changing the flow of water through the core. And the way the electricity is produced is shown here, and in this case the coolant water can be used directly to drive the turbine, and then this water is then condensed. So this is some variations on the reactors for light water reactors, either a pressurized water reactor or a boiling water reactor, but they both operate through boiling water and using that steam that's produced to drive a turbine and produce electricity. The boiling water fuel assembly is shown here. The fuel pellets are stacked in cladding tubes made of zircaloy, which is a zirconium-based alloy. These fuel rods are on the order of 3.5 meters. They're put into square lattices, either 8x8 or 9x9. And the water flows up along the fuel, and the rods are housed in a channel box, or also called a duct, as is shown here. And the zircaloy alloy is shown here. It contains zirconium, some tin, iron, chromium, and nickel. Another type of reactor is the CANDU reactor, which stands for Canada Deuterium Uranium Reactor. This reactor is cooled and moderated with heavy water, and this exploits the difference between the neutron absorption of hydrogen isotopes. Protons absorb neutrons to a much larger extent than deuterium. Therefore, one does not need to enrich the uranium in a reactor that uses heavy water as a moderator and as a coolant. The outlet temperature of this reactor is around 300 degrees C, and the core height is around 6 meters and a diameter of around 6 meters. And here's an example of a CANDU core with person shown here. The fuel rods can be put in and put out of this assembly while the reactor is operating. So you have the option of doing online refueling for a CANDU reactor. The fuel assemblies are shown here. Your fuel pellets, for instance uranium dioxide, are placed into these bundles, and these bundles can be moved into the reactor vessel. Here's an example of what the fuel looks like after it's been in the reactor. The cladding is again a zircaloy alloy, and the fuel pellets are uranium dioxide. And here is an example of the refueling machine. So one can refuel this reactor online, which would mean that the reactor does not need to be shut down and can produce electricity while it is being refueled. The three previous reactors, the heavy water and the light water reactors, are responsible for the bulk of the existing power reactors. However, other designs have been explored and studied, and we'll discuss some of these in the next few slides. One type of reactor is a liquid metal cooled fast breeder reactor. This is a pool type reactor. So again, you have fuel, and this fuel can be oxides, nitrides, carbides, or metals of, for instance, uranium. And the difference with this reactor is that the coolant is a metal, is a liquid metal. So it can be sodium metal, lead bismuth. And the reason one would have the metal as a coolant as opposed to water is that the metal does not moderate the neutrons, and the neutron energy stays high. So these are fast reactors. This allows fission to be induced on uranium isotopes that include uranium-238, not just uranium-235. So this is a way of both using uranium-238 as a fuel source and also breeding in plutonium from the uranium. So that's where the breeder reactor comes in. And again, similar to the pressurized water reactor, you have a metal fuel, which is liquid. This takes the heat from the fission process, goes to a exchanger where the heat from the metal fuel is transferred to water, and this water produces steam and then goes to a turbine. And this turbine is used to produce electricity. And there are two types that are shown here. Here's the pool type of reactor and a loop type of reactor. The pool type of reactor is larger and can often utilize natural circulation, where the hotter cooled material can go to the surface and the cooler coolant sinks down, creating a natural circulation. These can operate at higher temperatures, up to 650 degrees C, and they also need to make sure that there's compatibility of the materials with the coolant material. These fast reactors with metal coolant often use metals as fuels. An example of a metal fuel can be a uranium zirconium alloy. One reason why you'd want to alloy the material, if one looks at the phase diagram, uranium has a relatively low melting point. By making the alloy with zirconium, the melting point increases, and the behavior of the material itself is more suitable to the behavior in a reactor. So swelling and damage from the neutrons seems to be moderated if one uses an alloy as opposed to pure uranium metal. The metal fuel also has some beneficial behaviors when compared to oxide. Oxides are hard and brittle, and the metal fuel is plastic during irradiation, so it's a little bit more flexible, less likely to crack. The metal fuel also swells at low burnup due to the accumulation of fission products. This swelling is both axial and radially. This is a situation where one would have to produce a fuel that has gaps in it or smear density. So when this swelling occurs, the fuel can swell without colliding against the cladding material. At around 2 atom percent burnup, the fuel contacts the inner cladding wall. Fuel chemical cladding interactions can occur. As the burnup increases, so you're burning more of the uranium fuel, the fission gas bubbles become interconnected, and there's a pathway for the release of fission gas from the fuel into the fuel pin. So often metallic fuels will have a gap at the top that allows this fission gas to release and collect into. And some of the limiting lifetime factors for metallic fuel are the cladding and duct distortion. So in other words, as the fuel keeps swelling and if it keeps bending into the cladding material, this is a not desirable property and one would have to change out the fuel. And any strain due to pressurization of the cladding due to the fission gases and this fuel chemical cladding interactions. Also, the metallic fuel is better at conducting heat than an oxide. So from another reactor component point of view, the metal fuel can be better at producing electricity since the heat can more easily escape the fuel region to the coolant region and then be used to generate electricity. Here's an example of some swelling and fission gas release in metal fuel. During fission, 2 atoms replace every uranium or plutonium atom that is fissions. 25% of the fission products are gases, krypton and xenon. This generation of the fission products drive the fuel swelling. The gases that are produced, for instance krypton and xenon, coalesce into bubbles. That also accelerates the swelling, and the fuel swelling tends to reduce or close any gaps that are initially put into the fuel to prevent its interactions with the cladding material. As we mentioned in the previous slide, the fission gas can release. This can reduce some of the pressures into the fuel, but it pressurizes the plenum, or the area above the fuel, in the cladding. And here's an example of some uranium, plutonium, zirconium fuel at different burnups. At 0.9% burnup, you see that there's this gap between the fuel and the cladding, whereas at 17% burnup, so 17% of the uranium and plutonium has fissioned, the fuel is now pressing against the cladding material. And then you can see a micrograph of the fission bubbles in the metallic fuel. Another reactor variant that has been explored is the gas-cooled fast reactor. This is a fast spectrum reactor, so there's no moderator. One of the coolants that's been evaluated has been helium. One of the benefits of a gas-cooled fast reactor is the high outlet temperature, up to 850 degrees C. This can be useful for producing electricity, but it can also be used as a heat source for chemical processes. The fuels that are used in this are uranium or even plutonium materials that are ceramic. They can be particulates that are dispersed, or they can be a ceramic clad. And there's some possible configurations include pins or plate assemblies. One type of gas-cooled fast reactor is the TRISO-based fuel reactor. This TRISO reactor has a fuel core, as shown here, and this fuel is covered with a coating of graphite and silica carbide. This locks the fission gases and fission products into this little particle. So you can almost think of that each little particle acts as its own containment. These particles can be pressed into compacts, and these compacts loaded into fuel elements, and then these fuel elements placed into the reactor and then cooled by gas. A molten salt reactor is another variant of a reactor. In this case, the fuel is in liquid form. As we've shown earlier, an example of a molten fluoride salt is a lithium, beryllium, uranium fluoride. At room temperature, it would be a solid, and then as it heats up from fission, it can go to a liquid state. The fuel melts between 450 and 550 degrees. That would depend upon the exact composition of the fuel. In addition to uranium fluorides, one can also add thorium fluoride to this system to breed in uranium-233. Uranium chlorides can also be used as fuels. These could be trichlorides with sodium chlorides, uranium tetrachloride with sodium chloride, or even a mixture of the tetrachloride, the trichloride, and sodium chloride. There are two primary differences between the uranium fluoride and uranium chloride systems. One, the fluorides have different chemistries, and including the fact that the chlorides can have the trivalent and the tetravalent uranium states, so the overall chemical potential of that fuel can be different. And from a neutronic point of view, the fluoride is better at moderating neutrons, so the chloride reactors can have faster neutrons. The fission occurring in the liquid generates heat. That heat is then transferred to a salt coolant, and this coolant can be something such as sodium chloride, magnesium dichloride, sodium chloride, potassium chloride salts, and that coolant salt that uses the transferred heat to generate electricity with turbines. There are some variations in the molten salt reactor. Systems can have online chemical treatment to remove fission products and improve the efficiency of the reactors. They can breed in uranium-233 from the neutron capture on thorium-232. As shown here, thorium-232 can capture a neutron, produce thorium-233. That thorium-233 undergoes beta decay to protactinium-233, and then that protactinium-233 decays to uranium-233. This system can often uses chemistry to isolate the protactinium, allow the protactinium to decay in, producing the uranium-233, and then that can be added back to the reactor. Some molten salt reactor systems have a confinement of the salt. In this case, here's an example of a pool type reactor where the molten salt would sit here. There would be heat exchangers between the fissioning salt and the coolant salt at this point, and then that coolant salt would go out to an exchanger with water to produce electricity. And there could be variations in the salt compositions. We talked about lithium, beryllium, fluorides, but some systems have also explored zirconium fluorides. And with the chlorides, it's usually the uranium chlorides along with sodium chlorides. A final example of a reactor type in this lecture is one that's used for propulsion. Again, the fuel is used. This type of fuel is very similar to the triso fuel that we discussed earlier for the gas-cooled reactor. The fuels are placed in fuel elements, and then the reactor is assembled, and it actually looks something like this on the back of a rocket. The way this reactor operates to produce thrust for a rocket is through the use of hydrogen. Versus hydrogen, in a cooled state, is introduced into the reactor from a storage dewar. The hydrogen gas is heated and accelerated by the fission heat, so it passes through the reactor, very much like a gas-cooled reactor. This accelerates the hydrogen, and that is used to propulse the rocket. So the nozzle directs the kinetic energy of this system. The assembly, the reactor is placed here. The gas would be passed through. Here's your hydrogen feed tank. passes through the reactor and passes out the nozzle, propelling the rocket forward. Again, the fuel particle that is proposed for this system is very similar to the triso type of fuel, relatively small diameter, high melting point, and retains the fission products. It's made up of graphite with uranium dicarbide dissolved into the graphite matrix, and it's fully enriched uranium. The reason one for a rocket would prefer to use fully enriched uranium as opposed to 5% is that you can make the reactor smaller, so for rockets that is an important component. The way this reactor to be used to propel space vehicles would be that the vehicle would already need to be in Earth orbit. The principle operates by accelerating light mass to high velocities using the nuclear fission heat, so that's why helium is chosen. The high exhaust velocities make for more effective use of light mass propellant. The coolant can enter at 40 K and leaves at about 3000 K. There's some frit material that the gas needs to pass through. There's a few choices that have been explored, including rhenium, boron nitride, and some coated carbon. There's a cold frit material that needs to retain some of the reactor components. And the coolant is about 18% of the total moderation. Other moderators of choice include aluminum and hydrocarbons.
That completes Lecture 1, where we discussed the type of reactors, some concept of reactors. It's part of the lecture on the radiochemistry in reactors. When you've completed this part, please go on to Lecture 2, where we'll talk about speciation in irradiated fuel, utilization of the resulting isotopes, and then some overview of fission product chemistry in reactor systems.